So today we're going to be talking about the initial value problem and diving further into what a solution to a differential equation actually entails, and some stuff about the existence and the uniqueness of a particular solution. So let's just define what the initial value problem is. And so the initial value problem is basically a problem where we're told to solve for the solve for an equation that satisfies like a certain differential equation in this form. So we have some nth order diff eq, and we know it's a function of x, y prime, all the way to n minus 1, right? And then we're given certain constraints, and these constraints are basically, we know n values of y. So like y of x of 0 is equal to some value, y prime of x of 0 is equal to y1, and then we're given y n minus 1 x of 0 is equal to y n minus 1. So we're essentially given like a point for a specific point x, we're given its values for all of the derivatives, including the original function y. So we're given this problem, and the initial value problem is essentially given these conditions, find out, so given these initial conditions, find a satisfying equation. Okay, and so we will focus on something called first and second order IVPs, and it's pretty guessable, but it just means that the first and second order just means the order of the highest derivative. So a first order IVP is simply something in the form of dy by dx is equal to some function of x and y, and then we're given subject to one point. So y of x of 0 is equal to some value y naught, and then a second order is simply the order of our diff eq is higher, and so we have more variables on the right side. I switched these orders up, but it shouldn't matter. And then we're given 2 points, right? I think it's kind of intuitive. If you only had like 1 point, you wouldn't be able to find a particular solution. You'd have to find like a family of solutions. Okay, so we're mostly focusing on first and second order initial value problems because it's easier to kind of visualize, but you know, it can become arbitrary to the nth order like this. And usually like the way that you solve it is you solve for like the general like nth parameter family, and then use initial conditions to solve for variables. And this will make more sense as we do some examples. So let's just do some examples. And so let's say that given that y is equal to c e to the power of x, where c is just some variable, is a one parameter. So one parameter just means you have like one variable, c in this case, right? That can change. One parameter family of solutions for y prime is equal to y. And we're saying that our initial condition is y of 0 is equal to 3. Then like let's find a particular solution. And so it's pretty intuitive, right? We know that this is a certain point, and it just becomes like solving for c. So y of 0 is equal to 3, so we know 3 is equal to c times e to the power of 0, and then that implies that c is simply 3. And so our solution is y is equal to 3 times e to the x. Right. Note that now if our initial condition was like y of 1 is equal to -2, for example, then it would be -2 is equal to c to the power of e, right? And then our value for c is simply -2 over e is equal to c, right? And when we kind of graph out these, we graph these out, right? Our first solution looks something like this, right? We have this as 3, and then y is equal to 3 times e to the x. Whereas our second graph looks more like where it goes through the point 1 comma -2. So notice how the initial condition actually changes the geometric like solution, right? These are two very different solutions that both satisfied y prime is equal to y, but had different initial conditions, and those different initial conditions is what caused our solution to look pretty different. And that's like kind of like an important takeaway, where you can have multiple explicit solutions that map to the same diffie-q, and so because of that, the initial condition can sometimes help us find a unique graph. We'll see later that this uniqueness of like the fact that given initial condition, given the diffie-q, there still can be multiple solutions, and we'll see that later on. But this brings a point about the difference between a function solution to a diffie-q and solution to a initial value problem. So let's just talk about a function. So function is probably something that we're most familiar with, and so a function is something like y is equal to, or for all of these, let's just consider y is equal to 1 divided by x squared minus 1. And we know the graph of that will look like this. We have two vertical asymptotes. One is at x equals 1, and the other one is at x equals -1. And then when x is positive, or when x is greater than 1, we have this sort of graph. When x is between -1 and 1, we have negative, and then we're positive once again over here. Okay, and so our function is this whole curve, right, in -infinity to infinity, where we're not defined at x equals 1 and -1, but it's the whole curve, and it's the solutions that are defined over all sets of reals, right? Whereas if we're considering the solution to a diffie-q, recall that a solution needs to be defined, or needs to be continuous on the interval specified, right? And we see that just plainly having like y is equal to 1 divided by x squared minus 1, we have two discontinuities. So this whole -infinity to infinity cannot be the solution. But what we can do is we can say that the solution is y is equal to 1 over x squared minus 1 on maybe -infinity to -1, or -1 to 1, or 1 to infinity. And depending on which interval we define, we're going to just have we're only going to have a separate solution, right? So if we're talking about the solution between -infinity to -1, we're only worried about this curve right here. The rest of it doesn't matter. And likewise for the other intervals, 1 to infinity or -1 to 1. Now, finally, a solution to an initial value problem, right? And I think one thing that could particularly help is the differential equation for all of these is y prime is equal to 2x y squared. So this differential equation is like this equation satisfies the given differential equation. And when we're given this problem, this differential equation over here, and we're asked to solve, we need to specify one of these functions, and we need to specify one of these intervals, and depending on the interval, the solution is different. But if we're just given this function, we know that this whole set is what we're valued under. Now, if we're given an initial value problem, right, we're given the differential equation, right, and we're also given more constraints, where we could be given something like y of 0 is equal to -1. And then we know that, like, just looking at the graph and observing, that's this interval over here. So it's going to be, the solution is 1 divided by x squared minus 1 on the interval -1 to 1. So we're no longer ambiguous about which interval we're worried about because the initial condition is defined in the middle interval. And so the rest of the intervals from 1 to infinity and -1 or -infinity to -1 is not valid for our particular initial value problem. So hopefully the three the difference between functions, solution to a diffie and solution to an IVP made sense. You can kind of think about how each of these, as we go down from 1, 2 to 3, we're getting more and more specific because we have more constraints, and that kind of stops us, that kind of constraints our intervals even more and more. So let's do another example. Let's say that the function x is equal to c1 cosine 4t plus c2 sine 4t is a two-parameter family of solutions for the diffie q x double prime plus 16x is equal to 0. And notice how x is the independent variable right now. Find a solution to the IVP where, again, we're given this diffie q, and so that's why we were given the explicit solution for it, or the two-parameter family, and then we're given two initial values. So x of pi over 2 is equal to -2, and then x prime of pi over 2 is equal to 1. And so again, this just becomes a problem of solving for these variables. So we know x of pi over 2 is equal to -2, so let's just plug that in. So -2 is equal to c1 cosine 2 pi plus c2 sine 2 pi. So this is 1, so -2 is equal to c1, and then x prime is equal to -c1 times 4 sine 4t plus 4c2 cosine 4t, and x prime of pi over 2 is equal to 1, which is equal to -c1 times 4 times sine 2 pi plus 4c2 and then cosine 2 pi. And so 1 is equal to 4c2, and so c2 is equal to 1/4. And so our solution is x is equal to negative 2 cosine 4t plus 1/4 sine 4t. And the last thing is we want to find a maximizing interval. But notice how our equation is a sum of two sinusoids, and so we don't have any discontinuities starting from our initial value at point x is equal, or t is equal to pi over 2, and so we're defined on the entire range, right? Now, if we were dealing with tangent functions, we would have to provide a more strict interval. Okay. So the final thing we'll talk about is this idea of existence and uniqueness of a diffie-q. And the idea of, let's just cover existence. So existence is basically given diffie-q dy over dx is equal to some function f of xy. Do we have a solution? And do any of those curves pass through our initial point x0, y0. So first it's like, does this even like map to a certain explicit formula? And given that explicit formula, do any of them actually even go through our initial value? So that's the whole idea of existence. The next thing we're concerned about is uniqueness. And uniqueness just says that, are we sure that only one solution curve passes through point x0, y0. So the interesting part about differential equations are we can have a case where there are multiple curves and multiple curves go through our initial point. So we're not guaranteed that a specific initial value problem with the constraints and the diffie-q actually lead to just one solution. And that's important. There could be multiple solutions. An example of that is the equation y is equal to 0 and y is equal to 1 over 16 times x to the power 4. Both satisfy our diffie-q, or our initial value problem of dy over dx is equal to x times y to the power of 1/2, and the initial condition of y is equal to 0 is equal to 0. And let's just work through it. Y. So y is equal to 0 means y prime is equal to 0. And so dy over dx is always 0. And so this is true trivially. And then, we already got the satisfaction of the initial condition. And then the second solution that we have, y prime is equal to 1 over 4 times x to the third. And so dy over dx is equal to x times y to the 1/2, which is equal to 1 over 4 times x squared. And that's equal to x to the power of 3 times 1 over 4. So we satisfied the left and right side. And so we see that we've just given two separate solution curves that both satisfy our initial value problem. So that's an example of uniqueness not necessarily being true. And so can we figure out when we're guaranteed the existence of a unique solution? So when we're guaranteed existence and uniqueness. And in general, the proofs of existence and uniqueness goes per type or family of diffq, and it is pretty complicated, but let's just, and there's like different theorems and different conditions, and so let's just talk about if our diffq is in the form dy over dx is equal to f of x comma y, and then y of x is 0 is equal to y of 0. So if we recall, this is our first order IVP. Then we have a theorem, and the theorem says let R be a rectangular region in the xy plane. So where x is greater than or equal to a, less than b, and then y is less than or equal to d, and then greater than c. Containing x of 0 comma y of 0, so just containing our like initial point. If f of x comma y and the partial derivative of f with respect to the partial derivative of y are continuous on R, then there exists a interval I naught. So that interval can be defined by this range between like where the center is our initial point, and yeah, h is greater than 0. Inside our like bigger range of a comma b, where a unique function y of x is the solution to our IVP, right? So to put this into like a visual, let's say our rectangular range is this. So this is C, this is, or well, this is C, this is D, and then this is A, this is B. So we have some rectangle, and then if the partial derivative of our function with respect to y and f of x, y is both continuous on this rectangle, then within, and this is x0 over here, then there is like some interval where like, and it could be just like this interval where we have a unique function that satisfies our initial value problem. And so let's apply that to this example that we saw earlier, where we saw that the function f of x comma y is equal to xy to the power of 1/2. We knew that that was on x is on y, like on our initial value of f of 0 is equal to 0, not unique, right? But when is this solution unique is the question we're trying to ask. So let's find the partial with respect to y. So that's simply equal to x divided by y to the power of 1/2 times 1/2. Okay, and so this function is continuous on 0 to infinity or negative infinity to 0. Therefore, if initial point was on one of these intervals, we would be able to conclude that our solution of this is unique by the previous theorem, right? And let me just flash the previous theorem, because the partial will be continuous, and then that original function, we already know it's also continuous in that range, between 0 and infinity, and negative infinity to 0. And so because of this theorem, we're kind of guaranteed that the solution is unique. And so this only works, or like that theorem only applies towards our first order initial value problems. Different initial value problems might have different existence uniqueness theorems, but sometimes it's important for us to kind of guarantee the existence and uniqueness. And then the final thing to note is that the interval over which we have interval of existence need not be the same as interval of uniqueness. And the previous theorem is sufficient but not necessary. So we can have functions that don't satisfy the conditions of the previous theorem, but we can still get a unique solution to an initial value problem because of the fact that it's sufficient but not necessary. But if we have some function that satisfies those conditions, we can always guarantee the fact that we have a unique and existing solution.